Today, we're going to dive into the origin story of a technology that might just redefine the absolute limits of what we can compute. And look, this isn't just about building faster computers, it's about a totally new way of thinking about information itself. This is the story of quantum computing.
So, the first and most obvious question is, why? I mean, we have incredibly powerful supercomputers already, right? Why would we go to all the trouble of inventing something brand new from the ground up? Well, the answer really gets to the very heart of why this field even exists.
And the answer is actually pretty simple. It turns out there are certain types of problems in medicine, material science, even fundamental physics that are so monstrously complex that our best supercomputers would literally take billions of years to solve them. We've basically hit a wall with our current approach, and to break through that wall, we need a whole new kind of tool. To get our heads around this new tool, we have to start with the absolute basics. You know, the phone in your pocket, the laptop you're using, they all run on classical bits. The best way to think of a bit is like a light switch. It's either on or it's off, a 1 or a 0. Simple. A quantum bit, or what we call a qubit, is, well, it's more like a dimmer switch. It can be fully off, which is a 0. It can be fully on, which is a 1. Or, and this is the mind-bending part, it can be in a mix of both states at the same time.
Now this dimmer switch thing has a name. It's called superposition. It's one of the weird but totally true rules of quantum mechanics. And by taking advantage of it, a quantum computer can explore a huge number of possibilities all at once, giving it a kind of parallel processing power that classical computers just can't even dream of.
So where did this absolutely wild idea even come from? Well, you might be surprised to learn it wasn't dreamed up in a computer science lab. To find the real origin, we actually have to go back in time, into the world of theoretical physics, the quest to understand how our universe works at the most fundamental level.
Way back in the early 1900s, you had giants like Max Planck and Albert Einstein who were figuring out that the world of tiny subatomic particles plays by a completely different set of rules. I mean, it was totally counterintuitive. Particles could be in many places at once. They could be weirdly connected across vast distances. It was a strange new reality, and it laid the groundwork for everything that came next.
Okay, let's fast forward to the 1980s. For decades, quantum mechanics was this fascinating theory, but it was mostly stuck in physics textbooks. And then, a few visionary thinkers started asking a really radical question. What if we could actually use these bizarre quantum rules to compute?
And nobody, I mean nobody, put it better than the legendary physicist Richard Feynman. He basically said that trying to simulate quantum systems, like a complex molecule for a new drug, on a classical computer was just a waste of time. It's like trying to build a Lego model of a cloud. His point was simple but powerful. To truly understand a quantum world, you're going to need a quantum machine.
Right around the same time, another physicist named David Deutsch took Feynman's core idea and gave it a rock-solid mathematical foundation. He laid out the blueprint for what a universal quantum computer could be, really establishing the theoretical bedrock for the entire field. He proved it wasn't just a fun thought experiment. It was a totally new and plausible form of computation.
So by the time the 90s rolled around, the theory was there. But, a theory is one thing. Proving it can actually do something useful that a regular computer can't, that's a whole other ballgame. This was the decade that gave us the proof, thanks to some truly game-changing algorithms. You see, up to this point, quantum computing was a pretty niche academic thing. But then, in 1994, an algorithm got published that sent absolute shockwaves through the worlds of math and even national security. It instantly turned this little curiosity into a really urgent priority. That incredible breakthrough was Shor's algorithm. Now, what it does sounds kind of simple. It's just really, really good at finding the prime factors of huge numbers. But the implications of being able to do that one thing, they are absolutely massive.
Here's why this was so revolutionary. It's all about time. A task that would take the most powerful supercomputer on the planet billions of years to complete could, in theory, be solved by a quantum computer in just a few minutes, or maybe hours. We are not talking about a small speed boost here. This is a fundamental, reality-bending leap in power.
Okay, so I know what you're thinking. Factoring numbers? Who cares? Why does this abstract math problem matter so much in our daily lives? Well, the answer is pretty much everything. The entire security infrastructure of our digital world, the encryption that protects your emails, your online banking, all your private data, it's all built on one core assumption, that factoring huge numbers is impossibly hard for regular computers.
Shor's algorithm proved that a quantum computer could shatter that assumption, and in doing so, it could break most of modern cryptography.
And it wasn't just a one-trick pony. Just a couple of years later, another algorithm from Love Grover showed a huge speed-up for searching through massive, unsorted databases. With these killer apps now identified, the potential was undeniable. The global race to actually build one of these things was officially on. So, this is where we shift gears. We move away from the clean world of algorithms and theory and into the messy, incredibly difficult world of engineering. I mean, how do you even begin to build a machine that can control the wacky behavior of individual subatomic particles?
The challenges were, and honestly still are, enormous. These qubits are unbelievably fragile. They exist in this delicate quantum state that can be completely destroyed by the tiniest vibration or the slightest change in temperature. This breakdown process is called decoherence, and it's where the qubit basically loses its quantum magic and just collapses into a boring old regular bit. So trying to prevent that is just an extraordinary engineering feat.
But progress, even though it was hard-won, has been steady. In the 2000s, we saw the first little processors with just a handful of qubits. Then, in the 2010s, things really started to heat up. Big players like IBM and Google jumped in, pouring tons of resources into the problem and rapidly scaling up the qubit counts. And all that work led to a huge moment in 2019.
That moment was the declaration of a milestone that's often called quantum supremacy, or sometimes quantum advantage. This is the critical point where a quantum computer successfully does something, anything really, that is practically impossible for even the world's most powerful classical supercomputer.
And that's exactly what happened. Google's Sycamore processor performed a very specific, custom-designed calculation in about 200 seconds. They estimated that the same problem would have taken the fastest supercomputer on Earth about 10,000 years. Now, the problem itself didn't cure a disease or anything, but that wasn't the point. This was the critical proof of concept. It was the hello world moment for the quantum age.
And that brings us to today. The field is rapidly moving from these specialized academic labs out into the real world. We've proven the potential is there. Now, the hard work is all about making these machines bigger, more stable, and finally applying them to solve actual, real-world problems. So what's next on the horizon?
Well, the potential applications are nothing short of transformative. We're talking about things like simulating molecules to design life-saving drugs in a fraction of the time it takes now, designing brand new materials for hyper-efficient batteries or solar panels, developing unbreakable codes, and of course, breaking existing ones, and solving these mind-bending optimization problems for things like global shipping routes or financial markets.
So this all leaves us with one last really big thought. The classical bit, the simple on or off switch, gave us the information age and completely reshaped our entire world. Now we have the qubit. With its incredible ability to tap into the strange and powerful laws of the quantum realm, it's poised to do it all over again. The only question is, what new age is it going to create?